An exciting or fascinating of chemistry looking at the Nernst equation. What is the Nernst equation? Well, Nernst equation is a way to find the EMF, electromagnetic force, at varying conditions. Now, when Nernst first came up with he came with the Gibbs free energy at any condition is equal to Gibbs standard plus RT times the natural log of Q. Now, he didn't necessarily like that. They decided to work through it, and through derivation, he came up with this equation where the electromagnetic force at any condition is the standard electromagnetic force minus 2.303 RT over NF times the natural log of Q, where R is the gas law constant 8.314 joules per mole Kelvin, F is Faraday constant 96,500 joules per mole volt, N is the number of moles, and Q is the concentration of reactants or products. Reminder that concentrations only are for aqueous, and for gases, solids, and liquids do not have concentrations. Now, he also found out that most conditions take place at similar, what we call standard conditions. And since my R value, my N value, my F value are the same, we can symbolize the equation in what we call the standard conditions to be E equals E prime minus 0.0592 R over N times the last of Q. And what is standard conditions? Standard conditions is with temperatures 298 Kelvin or 25 degrees Celsius. So let's look at a problem. We have bromine plus lithium generating lithium ion plus 2 bromide ion. Determine the EMF for the reaction above at 28.5 degrees Celsius. The bromine ion concentration is 0.3355 molar and the lithium ion concentration is 0.5555 molar. So we look at a standard reduction potential to find the standard EMF. So remember, we take our reduction and our oxidation, and we're always in terms of reductions. So standard reduction potential for bromine is 1.09 volt. Lithium reduction potential is 3.04 volts. And since the standard is the reduction for the cathode minus the anode, we have 1.09 volts minus a minus 3.04 volts, or 4.13 volts. Okay, so we take since it's not at standard conditions, we take our first equation, E equals E prime minus 2.303 RT over NF log of Q, and we have our standard 4.13 volts, and 2.303 times 8.314 times 301.5 Kelvin, which is 28.5 plus 273, all over 2, since it's 2 electrons gained in 1, of course we have to multiply by 2. And then our Q value. Well, you look here, we have bromine as a liquid, so that's not going to have a concentration, and lithium is a solid, so our product reactants basically aren't going to have a concentration at all. We do have to balance it. So we're going to put lithium here out. So we end up with the concentration of lithium ion squared times the concentration of bromine ion squared. Put our concentrations in, multiply through, we get 4.13 volts plus a 0.044 volts. So we end up with 4.17 volts. That is my electromotive force at these conditions. All right, let's look at another problem. Get rid of this here, sorry about this. Okay, for the cadmium-silver reaction, going to silver plus cadmium, I'm determine the electromotive force at standard conditions if the concentration of cadmium is 3.545 molar and the concentration of silver ion is 0.7899 molar. All right, finally do this one. Calculate the electromotive force for copper-zinc reaction where the concentration of zinc and ion are 0.2555 molar and 0.3955 molar respectively at 46.8 degrees Celsius. All right, that's it. Take care. Be good.